So I am in the chemical engineering department, and knowing that this would be a diverse audience, at best, perhaps mainly electrical engineers, sort of as expected, I've tried to make the talk appeal to a broad range of people, so I hope that it comes across that way. The work that we're doing in my group at NC State is sort of interdisciplinary, and we're working on several different things. And what I'm hoping to do is sort of weave together three related stories that cover these three topic areas. And I'll let you know when I make a transition from one to the other, but hopefully it will be more or less seamless. In general, my group studies thin film, patterning, which is of course of interest to electronics, and soft materials. I'll explain that a little bit more as we get. So I'll start this story by pointing out what might be obvious about conventional electronics, and that is that they work very, very well, but they tend to be made out of rigid materials. So this is a guy holding a silicon wafer, printed circuit board. These are all familiar things to electrical engineers. And the idea of flexible electronics is taking the functionality that you see in conventional electronics and building it onto flexible or compliant substrate. And by doing so, that enables new applications. So of course, the military is interested in this. You can integrate electronics onto this uniform of a soldier. Imagine integrating electronics into textiles. I think this is not a real picture, but it's something I pulled from the web, but that gets your mind thinking. Imagine instead of a Kindle, you have something that feels like a newspaper, but still reads like a computer monitor. John Rogers, who's one of the leaders in this field, has done some really nice stuff with bioelectronics. And then Nokia is working on this product called the Morph, which is sort of science fiction at this point. But the idea is to have a cell phone that you could wrap around your wrist like a watch, and then unfurl it as a cell phone when needed. And so the typical approach to doing these things is to take materials that are considered to be rigid and then make them thin to make them flexible. So we have plenty of experience with this in our day-to-day lives. This is a 2x4, which is a great building material that used to make houses. But if you make it thin enough, you have paper. Same thing, aluminum is a great building material for bike frames and other things that have high strength. But if you make it thin enough, you have aluminum foil. But there's some common features of these, and one is, of course, that they're not stretchable. They're not inherently stretchable. They're still stiff materials. They're just flexible because they're thin. And then the other is that as you flex them, you tend to have fatigue, which can lead to breaks. And so an example of this is shown here. So this is a cross-sectional cartoon of, imagine a metal film on a plastic substrate. And as you bend it back and forth, eventually the metal film will crack and lead to degradation of performance. So we had this sort of wacky idea of using liquids to replace these conductive components. And the idea is that liquids flow in response to stress, and so they're not going to crack or fatigue. But they have all sorts of other challenges. For example, they can undergo instabilities. And you see this if you turn on a faucet. A cylinder of water will break into little droplets because of surface tension. So it's difficult to control the shape of a liquid. So that's a big problem. Evaporation, liquids tend to evaporate and kind of go away. And then they may not have the right electronic properties. So we're interested in conductors, and the first thing that comes to mind when you think of liquid metals is probably mercury, which is toxic. But also it has this problem that it tends to beat up. Now this is a statue that's in Chicago, but it illustrates a point that I'm trying to make, which is because of the high surface tension of mercury, it tends to want to form a sphere. And what we would really like to do, if you've ever seen the movie Terminator, is to mimic this evil character from Terminator 2, which can sort of morph its shape into non-spherical shapes. And hopefully I'll convince you today that we can sort of do this. So this is the key slide, the first part of my talk. This is a series of images going from left to right of a drop of liquid metal that's in between a rigid substrate and a syringe tip. And all that's happening here is the syringe is being withdrawn away from the substrate. And there's a couple things that I want to point out. First is that the metal sticks to the substrate, which is not all that unusual. There are other liquids that stick to the surfaces, but mercury would not necessarily do this. And the other thing is, as you stretch it, it sort of breaks like bubble gum. And when it breaks, it actually bifurcates. It forms two cone-shaped structures. So this image is not just captured in time. This is the stable structure that forms with this metal. And so I'm not telling you why this happens. I'm going to leave you in a little bit of suspense, and then I'll tell you in just a second. So you can be thinking about why this is. Let me show you one of several movies. This movie is just to show you how this metal behaves. This is a 2-inch by 3-inch glass slide, just a standard syringe. You can see that you can pump the metal out of the syringe, no problem. It's a low viscosity liquid, very much like water. But now you start to see something that's different than mercury. You can spread this out on the glass slide like wet paint. And then if you tilt the slide, you can see the metal flowing, sloshing back and forth, yet it maintains its macroscopic footprint. So it kind of holds its shape, it can still flow. And this is all at room temperature. Okay, so what is the material? We call it E-gain, and I will try to just refer to it as liquid metal to avoid confusion, but E-gain stands for eutectic gallium and indium. These are just things you can buy off the shelf, so it's not really a new material, it's the way that we're studying it. The reason that we use a mixture of gallium and indium is that gallium by itself, which is really the material we care about, it melts at 30 degrees Celsius, which is technically a solid at room temperature. By putting in some indium, you depress the melting point to below room temperature, and you therefore have a liquid. So the reason that we're studying this material, which again is not new, it's just the way we're using it and studying it, first and foremost, it's a liquid at room temperature. So that allows us to make things that are flexible and soft and stretchable. The viscosity is like water, so it flows very easily. It's commercially available, so we can just buy it. It's got low toxicity, basically no vapor pressure, so you don't have to worry about breathing it. And important for our research is we can control its shape. So I'm going to spend a little bit of time talking about that. But before I do, let me explain to you why it has this property. I've kind of left you hanging. And the reason is really simple. Like most metals, this metal on the surface will oxidize. So if you want, you can think of it as rust. It's technically not rust because it doesn't flake off. But it forms a layer of oxide. And aluminum does the same thing. So if you go to a store and buy aluminum foil, it's got a thin layer of oxide. But what's special about aluminum and this material is that it's so-called passivating, which means it forms and then doesn't get thicker. And that skin, which is only about a nanometer thick, allows us to control the shape of this material. And so to kind of convince you, this is a video where we've spread the liquid out onto a glass slide. And if you expose this to acid, you actually can remove the skin because it's so thin, it goes away very quickly. In fact, the vapors are enough to do it. And in the absence of the skin, it beads up just like you would expect mercury or any high surface tension fluid to do. Okay, so the key thing is we have an oxide skin of gallium. Just to prove it to you, this is Auger spectroscopy of the surface of the metal. And the take-home message from this is if you kind of do an elemental breakdown of the surface, you primarily have oxygen, gallium, and a little bit of indium. So again, indium is just there to lower the melting point. It's really gallium that we care about. And gallium has a lot of interesting properties, which I'd be happy to talk about at the end of the talk. Okay, so this is the only sort of chemical engineering-like slide, so bear with me. But I want to explain to you the mechanical properties of the metal. And so we use this technique called Rheology, and on paper it's a very simple tool. It's got a stationary bottom plate, and onto that you put a drop of the liquid. And then you bring down another plate, and you squish it, and you measure the torque required to turn the plate back and forth. So you can imagine that if you had water between these plates versus honey or something like that, it's going to be more difficult to turn this plate the more viscous it is or the more elastic it is. And so I like to call this geometry sort of like an Oreo cookie, where the cream of the cookie, in this case, is the liquid metal, and that's really the thing you're trying to measure. But it's a little bit more subtle than that. And if you take your Oreo cookie, so here's the liquid metal, and you do a cross-sectional view, the bulk of the material is a low viscosity liquid. And so from the rheometer standpoint, it can't even tell that it's there. The viscosity is so low. And so what you're really measuring is the mechanical properties of the skin which surrounds the fluid. And so to sort of give you an idea of what this looks like, I've got a short video. Again, we've got the liquid metal squished between two plates, one of which is stationary, and the top one which we can control using this fancy instrument. And we're going to tell the instrument to turn this plate to the right, to the left, and then we're going to let it go. And you're going to see that the skin, you're going to be able to see the skin, you're going to see that it has elastic energy. So here we go to the right, to the left, and then we let it go, and it snaps back just like a rubber band. So we can capture this or sort of quantify it in this plot. Let me walk you through this because you're probably not used to seeing plots of this nature. So this is G prime. This is what's called the elastic modulus. If you think back to freshman physics, this is very much like Hooke's constant. It tells you sort of how hard it is to stretch a spring. And this axis is surface stress. So this is kind of how hard you're pushing on that skin. And what we see is that low stress, the skin is elastic. So you can think about this again like Hooke's constant. But this is what's interesting. When you start pushing too hard, suddenly this drops very, very fast. And what's happening is you're breaking the skin. So if you push with force greater than this, the metal will flow. And if you push with less force, it will hold its shape. And so this kind of gives us a guide to allow us to flow the metal with certain pressures, but then have it stop flowing when you're below a certain threshold. Okay. So this video is just for fun. This is some unpublished work which we're hoping to submit maybe this week, in which we show kind of the amazing mechanical properties of this nanometer thick skin. So this is a drop of metal, and I'll play the movie in just a second, but explain what you're looking at. This is a syringe needle, a drop of the metal, and you can see that this metal has a little tip on it, which you would not get with water or with mercury. This is just completely from the skin. And a really amazing undergrad built this tool in my lab where you can take droplets and dispense them. That's not all that interesting, but now you see that you can stack them. And this is coming out of the plane. And these things hold their shape. So this gives you a sense of how fast the oxide forms. It basically forms immediately. But it's thin enough that the structures can merge together. And you can start patterning these things sort of direct right, metallic structures out of plane. Usually I get some oohs and ahs. You guys are tough. Okay, I'll try better. Okay. So a much easier way to shape this metal is using what's called microfluidics. These are basically just very small tubes. And we can do this very easily using a material that's sort of like bathroom caulk. It's called PDMS, but it's not all that important. We basically mold the material. So this is a squishy material, which we seal to another flat piece of the same material. And then we inject the metal. We literally do it by hand. You can use a syringe. It's extremely simple. And we formed a dipole antenna. Now, usually I'm talking to chemical engineers, and I have to explain that a dipole antenna is just two collinear wires. And it's very much like bunny ear antennas that you find on old-fashioned TVs. But surely this audience knows this better than me, so I'll just say that this was collaborative work with Sean Luca, and I'll probably deflect any, or reflect any, any questions to him. But what's cool about this is two things, well maybe three things. One is that usually when you form the wire and then you put the insulation around it. Here you form the insulation and then you add the metal, so it's a new fabrication paradigm. The second is that the mechanical properties of this adopt that of the polymer. So the metal itself is a liquid. It doesn't affect the mechanical properties. And then the third is that with an antenna, the resonant frequency depends on its shape. So we basically built a rubber band that's an antenna. And as you stretch the rubber band, you make it longer. And in doing so, you shift the frequency to lower frequencies. And when you let it go, it goes back. So you can think of the antenna as being tunable mechanically, but you can also think of it as being a sensor and an antenna at the same time. Turns out that I asked my student to try this thinking there was no way it would work, but it does. If you take a razor blade and cut one of these wires or antennas in half, and take the razor blade back out, it retains electrical continuity. And the reason it does it is because the metal oxidizes so fast that when you cut it, it neither flows out or back into the channels. And you can see that in this image. So this is a close-up of where the razor blade cut. So you can see this is kind of where it's fractured. This is the metal, this is the polymer, and you can see that the metal is flush with the interface so that when it comes back together, it retains continuity. Now, the problem with this approach is that you have to have some of the polymer intact in order to kind of snap it back together. So recently we thought, well, what if you use a self-healing polymer? Now you can not only make electrically healing structures, but you can make mechanically healing. So I have a French postdoc who has a flair for things dramatic. So he made this video. And this is a very simple circuit in which we have a wire. This is the liquid metal inside of a self-healing polymer. It connects to an LED, so now you see that it's turned on. You can then use scissors. These are just dull scissors, they're not particularly sharp. And of course, when you cut through it, you mechanically sever it, but you also electrically sever it. And so now you've broken the circuit. And you can see that the metal is still, well, it's hard to see, but you can see that the metal is still in the channels. And then when you bring them back together, if you have good aim, you can get the circuit to turn back on just by touching them together. But what's even more cool about it, or at least sort of the advance here, is that if you give it a few minutes, this is not a material that we developed, this is just something we're using. If you let this polymer sit for about 10 minutes, it will regain its mechanical properties. So you can stretch it and it's sort of self-heal. And on top of that, just sort of by stroke of good fortune, I guess, is this material is stretchable. So you can stretch it to about 2 times its initial length. So it's kind of cool. So taking this idea sort of one step further, is imagine that you have 2 circuits, as shown in this cartoon, that are completely independent, and suppose you wanted to rewire them. All you need now is a pair of scissors. You can cut these in half, and at room temperature, you just reassemble them. And so to kind of demonstrate this, we made a shape that was a diamond and a shape that was a square, and we swapped the wires so that we took these 2 independent circuits and now made one loop in which now both lights are turned on, whereas before you just have an LED just kind of sitting there. Okay, so one other just kind of fun video. We've also just recently made some very stretchable wires, and if I had sound, it would just be even more cool. But so we made an iPod headphone wires that are made out of a really stretchy polymer. So it's a tube filled with the liquid metal, and you can hear the sound. It's playing NC State Fights on. But as we stretch it to many 100% strain, there's no change in the sound of the quality of the music or the volume or anything like that. It's kind of fun. Okay, so what I've talked about so far is basically changing the shape of these metallic structures by stretching them, by making them longer. But because the metal is a liquid, you could also think about changing its shape by getting it to flow. And so as a simple demonstration of this principle, we made our favorite thing, which is a dipole antenna. And we made 4 collinear segments of metal, which is shown in this cartoon. So here's some metal, here's some metal, here's some metal, here's some metal. This is not at all the scale. But basically, because these are not electrically connected, you can think about these 2 innermost ones being a dipole antenna. And they're separated by a row of posts. So I always like to call these jail bars. Imagine if you're in the channel, you've got these jail bars that are preventing the metal from going through. When you apply a sufficient pressure, the metal can squirt through those posts and merge together. So now you can take a dipole that is this initial length and make it maybe 2 times its length, or you can make it and start as an inch and then make it a mile. Just depends how you design it. And so this shows. Well, let me just show you a video of how this works. So this is a zoom in of the black part is the metal, this is the metal, and the little circles are posts. So you're looking top down on these jail bars, and of course the metal is just happy to be there because there's an oxide skin that's stabilizing it here. No human intervention, it's just happy to be there. But then when we squeeze it with our fingers, the metal will squirt through these posts, merge together, and then kind of fill in the interstitial spaces. So now you have an electrical connection that connects these 2 wires. This whole video was taken with a high-speed camera, so that whole video lasted about 3 or 4 milliseconds. And by doing that, we can change the length of the antenna and change its frequency. So again, we start out with the black here is metal, so we've got 4 lines of metal and microfluidic channels. We merge the rightmost one together to make the length longer than the initial length here. And in doing so, we shift the frequency from a high frequency to a lower frequency to an even lower frequency as we make the antennas longer. And so I'll conclude this part of the talk just by showing you kind of a montage of other stuff that we've done, but won't discuss it at any length. I believe so I showed you the video of the stretchable wires. We've also worked with Jean-Luc to make his favorite structure, a coil for telemetry. We've also made patch antennas for GPS applications. We've made stretchable coax cables, so very much like the cables that you would use in your house for cable television. We've done some other stuff with microfluidics, which if you haven't worked on microfluidics, you might not appreciate this, but it's a very, very simple way to fabricate electrodes and microchannels. And we've also made, these are very little microspheres of the liquid metal, which don't have an immediate application, but are kind of cool nonetheless. Okay. So I'm now going to transition to the second part, second topic, which I'm going to do it by bringing back up this slide and pointing out another obvious thing about conventional electronics, and that is that they tend to be 2D because of the way that they're patterned. Again, they're made out of rigid materials. They use electrons, and they work in a dry environment. Now, contrast that to what I would argue is the most sophisticated electronic device, which is the human brain. And maybe not my brain, but many people's brains. And think about it. The human brain, just like other things you find in nature, like nerve networks or photosynthesis, use soft materials, so they're not rigid. They use ions instead of electrons. They're 3D instead of 2D, and they're wet instead of dry. Completely different. And not only that, but their operating principles are different. And so one of my colleagues, Orlin Bellow, was working with hydrogels. Now that word may not be familiar, but anyone who's had Jell-O has had a hydrogel. A hydrogel is just a polymer network, so think about it kind of like a sponge that has a bunch of water in it. And one of the reasons these things are interesting is because they're biocompatible. They're full of water, and so cells and biomolecules are very happy to be in these materials. So my colleague was taking these things and making electronic analogs out of them, like diodes and stuff like that. But he was making them not so interesting by slapping on rigid electrodes like copper and ITO. And so we very naively thought, well, if we take the liquid metal and combine it with the gel, we're going to have something that's entirely soft and squishy and aqueous-based and uses ions, and it's going to have a bunch of interesting properties. But something happened that we didn't foresee. And that is that at the interface between the metal and the gel, something very interesting happens. And so this is the experiment that I'm going to describe. This is a cross-sectional view, so this is the liquid metal. It's in contact with the hydrogel. Again, just think about this like a sponge full of water. And this is a transparent electrode, which allows us to look through and look onto the metal. So if you were looking through a microscope, this is what it would look like. This is a hemisphere of the metal. And I'm going to show you this video to show you what you would see if you were looking through the microscope. The metal, when you apply a reducing potential, removes the oxide layers. Okay, so you see there's this oxide layer. We apply a potential, the oxide layer electrochemically reduces. It goes away. And so in doing that, we can, depending on the direction of the bias we apply, we can either make the surface have this very thick and kind of gnarly looking oxide, which is a wide bandgap semiconductor, basically an insulator, or we can remove it and make it a conductor. And as a result, if you measure current versus voltage through this circuit, in the direction where we form this oxide, the current is passivating. It doesn't allow current to pass through very easily. Whereas when you go in the other direction, you remove the oxide layer and you get current. So this should be very familiar as diode-like. And so diodes, so let me just kind of, actually I'm going to skip this slide. This is maybe a little bit too much chemical engineering. This slide was just to kind of prove to you that the mechanism is indeed kind of what we see. So turns out that we can use this principle to make what's called Memristors. And this was a new topic for me, so hopefully this is familiar to all of you, but it's a really interesting story. This Memristor stands for memory resistors, and it's considered the fourth fundamental electronic element in addition to the resistor, the capacitor, the inductor, and now the memristor. And it was predicted, I think, in the 60s by a guy at Berkeley. And it wasn't until about 10 years ago that Hewlett-Packard was actually able to make one of these things. And it has this kind of feature, whereas if you measure current and voltage, the memory has two states, an on state, which is conductive, shown by this green line, and then something causes it to switch, and it goes into an off state, which is resistive. That's why we call it a memory resistor. They typically have a structure of metal, insulator metal, in which there's some event that causes a conductive pathway to form, so you can switch between a conductor and an insulator. Now, we've been able to do this using Jello, so to tell you exactly how this works. For a memristor, you have to have asymmetry. What I mean by that is the top of the device has to look different than the bottom. And in our Jello-like device, we do that by doping these hydrogels with polyelectrolytes. That's just a fancy word for ionic polymers. And we dope this red-colored layer with an acid-like polymer. So it has a very low pH, it's acidic. This layer, we dope it so that it is basic. So we now have asymmetry. The top layer, which has this metal contact, is now in contact with an acid, and the bottom part is in contact with the base. And that matters. And so I'll kind of walk you through how this works. This is a cross-sectional view of our device. We've got metal, acid gel, base gel, metal. And when you start out, you've got a very conductive pathway. You've got metal basically in contact with salt water. And so you start here, of course, at 0 volts and 0 current, and you start to sweep the voltage. And as you do it, you get a current. That's this scan here. So it's conductive. But in doing so, you start growing an oxide layer. And when you form that oxide layer, it becomes resistive. So now when you scan in the other direction, it's no longer conductive, it's now turned off. So we now have two states, conductive, resistive, on, off. When you go in the opposite direction, you reset the device and remove the oxide layer. Now the importance of the asymmetry here is regardless of these two states, the base prevents the oxide from growing here. Otherwise you would switch back and forth between a state where the oxide's here and a state where the oxide's here. But by making it asymmetric, we keep this interface always conductive, and we switch this one between conductive and resistive. So now we reset the device, and when we come back, there's some hysteresis because of charging and also electrochemical events, but the point is, you return it back into a conductive state because you remove the oxide layer. And then of course, when you sweep it back, the oxide layer regrows and it's resistant. So if you follow that, those of you that are students, you deserve a PhD because it took me like months to figure this out. Okay, so there's the on and the off state. And so we took this kind of to the next intuitive step, which was to make multiple junctions. So we made a 2x2 crossbar. So imagine 2 wires and 2 wires crossed like this. At their junction, we put the gels, and we showed that we can start with all of them turned on. We can turn one off while leaving the others on, turn it back on, and take another one, turn it off, turn it back on. So this just shows you can independently address each node. And again, I emphasize Hewlett-Packard is not shaking in the boots at this work, but it's made out of Jello, which I think is, okay. So I'm going to wrap up this portion of the talk by just sort of summarizing the work with the liquid metal, and that is that hopefully I've shown you that the metal has this elastic skin composed of oxides of gallium. That allows us to shape it into things like antennas, mold it into little droplets or cones, and we can actually control the thickness of this oxide layer to make memory devices that sort of mimic the human brain. Okay. So I'm now making a little bit of a leap of faith. This is not related to liquid metal, but I think you'll hopefully find it equally interesting. And this is an idea that is called self-folding. And the idea is to convert two-dimensional information into three-dimensional shapes. So if you think about it, there's tons of two-dimensional patterning techniques. Roll-to-roll processing, this is how newspapers are printed. Screen printing, the way that t-shirts are printed. inkjet printing, most of us have an inkjet or a laser jet access, or photolithography, the way that computer chips are made. These are all inherently 2D. So we developed a way to convert this two-dimensional information into 3D shapes using only light. And I'm going to show you a video first to give you an idea of what I'm talking about, and then I'm going to explain it. So this is, again, a 2-inch by 3-inch glass slide. This is a fraction of a penny worth of very inexpensive polymer that's been patterned with an inkjet printer. So this whole experiment costs about $5. And you're going to see a light bulb that's nothing special. It's an IR heat bulb, very much like the ones McDonald's uses to heat up French fries. You can buy them at Home Depot. And this is in real time. So you take the light bulb, shine it, probably buy it. Okay, you want to see it again? All right. Okay. So the idea is very simple. We take, I guess I'll play this video while I talk. We take a commercial polymer that's been pre-stressed. What that means is it was heated, stretched out, and then cooled. So it's trapped in a state that it doesn't want to be in. And if you put that in the oven, the whole thing would shrink. But what we do is we pattern it with black ink, literally toner from a desktop printer. And when we shine light on it, it gets hot faster than the rest of the polymer. And so it will relax the polymer and create stress that causes it to fold. And you can pattern the ink on either side, which I didn't realize when we did this, but I guess in the origami world it's kind of a big deal, because you can get it to fold up or you can get it to fold down, which are called mountain or valley folds. And yeah, so that's it. So we've been able to make a whole bunch of different shapes, again, folding both up and down, and making boxes and pyramids. And it gets even better. So not only is this a commercially available polymer, but it's actually a children's toy called a Shrinky Dink. If you've ever played with that as a kid. Those of you that haven't, this is a novelty toy. It's a polymer film that you can kids color on with special crayons. They then put it in the oven and magically watch while these things shrink down to about 50% of their initial size. So to give you an idea what this looks like, it starts out like a transparency film. So you can't even see it, so we box it here in blue ink. And if you shrink it, it shrinks 50% this way, 50% this way. And this particular variety gets a little bit hazy, but it's just a feature of this particular system. It's polystyrene. This is the same material used to make styrofoam cups, plastic petri dishes if you work in a lab. It's a very dirt cheap polymer. And the way that it's pre-stressed is the following. You take your polymer, which is just happy, and you heat it up above what's called the glass transition temperature. This is the softening point. So this laser pointer is made out of polymer. If I were to heat it enough, there's some temperature at which it would not melt, but it would become soft. I could start kind of deforming it. And at that point, you take this thing and you stretch it. And fortunately for us, this is all done commercially. But you stretch it, and the polymer chains are now stretched out. So they're in a state they don't want to be in. They want to be coiled up. That's their energetically favorable state. And so if you cool this down, you basically trap it so that it can't flow. And when you heat it back up, it reverses. It gets hot, it relaxes, and goes back to its original state. And so we're not the first ones to realize the utility of this fun children's toy. Some group at Michelle Klein's group in California came up with a way of making microfluidic channels by printing on a large area and then shrinking the features down, making them micro scale. Our idea again is to use localized heating, so you can see where the black ink is, you get some localized shrinkage, and of course the material has to go somewhere so it gets thicker. So just to kind of prove it to you, these are two sheets of exactly the same dimensions. This one's patterned with black ink, this one's not. We shine light on it for 40 seconds. This one stays the same shape. This one shrinks in plane in both directions, and of course gets thicker. And so we have an IR camera which allows us to track the temperature, the surface temperature of this polymer. And this one, which has no ink on it, of course it gets a little bit hotter with time, but not it never exceeds the glass transition temperature even after about a minute. Whereas the one that's coated quickly gets very hot. It actually levels off where it goes through this transition, which is about 100 degrees for polystyrene, and then continues to get hot. Okay. So again, a little dose of chemical engineering. Chemical engineers are very interested in transport. So diffusion, fluid transport, heat transport. And this is a heat transport problem, so it's a great chemical engineering problem. We looked at two variables that turned out to be the most important things. One was the hinge width, so just the width of this black line which we patterned by a printer, and the temperature of this hot plate. So that was kind of the dirty little secret in that video. That sample is sitting on a hot plate, which basically gets it really close to the glass transition temperature. And then when you hit it with light, it goes over the glass transition temperature and folds. Okay, so we did a bunch of measurements, and we sat there literally with a stopwatch and with our eyes, and we watched these things as they started to fold. And we measured the amount of time for it to go from here to just starting to move. We call that the onset of molding. And we showed this experimentally here in this plot, in which we vary two things, the hinge width, and what you see in this data is that the folding time decreases as the hinge width gets wider. And that should be sort of intuitive. The wider it is, the more energy you're delivering to the hinge, and the easier it is to fold. The other thing we varied was the hot plate temperature. And let's look at the two extremes. If you start at room temperature, bad things, well, not bad things happen, but it just doesn't work as well. It takes a longer time to fold, and you see big error bars on this plot. If you start at 90 degrees, which is very near the glass transition temperature of 100, it folds within about a second. So it's very dramatic because you don't have to heat it up as much. We then did a very simple model. And this is a cross-sectional view of the polymer. So you're sort of looking at it this way. And W, again, is the width of the hinge, or the ink. And when we shine light on it, you'll see that the top of this surface gets hotter faster than the bottom. So you see this looks a little bit red, this is a little bit yellow. And as a result, you get differential heating. So the top part gets hot, and it allows it to fold. And using only one fitting parameter, we model this. And that fitting parameter is the temperature of the surface when we see folding. And our model predicts both qualitatively and quantitatively the experimental trends that we see. Now here's where it was exciting for us. We went into the lab and used an IR camera and measured the temperature of the hinge when it starts to fold. So this is an IR camera image of the shrinking ink. And you see that it's sort of uniform everywhere except at the hinge. It's glowing red, which means it's hotter. And using this scale, we could show that the hinge was at about 120 degrees. That was the exact fitting parameter we used to fit our data. So in a sense, it wasn't even a fitting parameter, but it was just satisfying that we, without even knowing this result, we got a very accurate model. And so right now we're working on a bunch of things. One of the questions I often get is, can you unfold? And the answer is yes, but unfortunately you can only do it one time. So if you think about this is very much like a rubber band. If you stretch a rubber band and let it go, it's not going to automatically re-stretch back out. So it's basically what you're doing is you're going from this state, which is very energetically unfavorable. You're folding it. By the way, this is a grain of rice, just to give you some size scale. So we put it in this little container, and then we put the whole thing in an oven, and everything shrinks. So it goes from this initial shape to something about 50% in size. We also just had a really fun time. We got some origami books, and we had an undergrad who went in and just showed that you can make some more complex shapes. But the thing that I'm interested in is that if you can pattern things like electronic structures in 2D, and then this is just really kind of hokey, but we formed a S to represent the state block S, and to show that by patterning in 2D and shining light, we can basically get this thing to fold up, and then the panels to fold over. So now you can start thinking about this as a way to assemble in a hands-free manner electronic structures like resonance structures, etc. And so in conclusion of this part of the talk, hopefully I've shown you that folding, that this is a really simple folding technique. It depends on the localized absorption of energy, and it allows us to convert 2D patterns into 3D shapes. So this is a picture of my group from last summer. A lot of the work has been collaborative, and I hope I've acknowledged people as I've gone. Of course, Jean-Luc, who you all know well. The stuff with the gels was done with Orlin Bellows, who I think I acknowledge. Jan Ginter is involved with folding, and everyone else that I've listed here are students. And with that, I'd be happy to take any questions. And thank you very much for the invitation and the attention.
We have a few minutes for questions.
You mentioned earlier that your liquid metal can go down to about 15 degrees Celsius. Now, I guess, have you looked into, or are there any metals that stay liquid below that temperature? Because that's like, exactly 15 degrees.
Yeah, so there's multiple ways to answer that question. The simplest way if you wanted to push it lower is there's other alloys. So gallium alloys is a bunch of different things. The most famous one is called gallium. It's gallium, indium, and tin. And that pushes the melting point even lower. The reason we don't use it is purely an academic one. We've been studying gallium and indium, and we know everything about its surface, and we just continue to use it because it's really the gallium oxide skin that matters. So other gallium alloys are going to have probably a gallium oxide skin, and everything that you saw here could be applied to them as well. The other way to answer that is that one of the many interesting properties I alluded to about gallium and its alloys is that it supercools like crazy. So to give you a familiar material, think about water, right? If you put water in the freezer, it will freeze as long as it gets below 0 degrees. You can supercool water about 3 or 4, maybe 5 degrees below its freezing point, so negative 3 or 4 or 5 degrees Celsius. But after that, there's just too much driving force and it will solidify, turn into ice. This stuff, which technically melts and freezes at 15.7 degrees Celsius, you can take it like 60 degrees below its freezing point. Yeah, so it's actually very difficult to get it to freeze. We've left this in a freezer at negative 14 degrees Celsius for a week, and it was still liquid. So I think about that number more as a melting point. If you have a liquid, you have to go to 15.7 to melt it. But going the other direction, it's actually quite difficult to freeze it.
Yeah, question.
Look like the shrinking material is always uniformly shrinking to can you get material that's isotropically?
Yes. Yeah. So we started with that just because it's off the shelf. We're now working with material from Eastman called Embrace. It's the material that they use to print Gatorade the labels for Gatorade bottles. So they print them in 2D, and then they wrap around the Gatorade bottles and hit them with like a hair dryer, and it just shrinks and wraps around the bottle. And what's interesting about that, if you just have uniaxial strain, which most of these things actually are uniaxial, you can align the hinge. So imagine if it's stretched this way and you put the hinge here. When you heat it, it's going to want to shrink back this way, and it will just fold just like everything you saw here. Now imagine you stretch it this way and you align the hinge this way. Now it wants to shrink, but it really can't because the panels are sitting there and are rigid and don't want to shrink this way. And so what that does, it ends up creating stress in plane, and you can get it to fold. So we've been able to make something that kind of looks like a bubble gum wrapper, where it folds into a cylinder, and then it's kind of wrapped.
Or you can imagine what the center.
Yes, it looks like a yo-yo where it's kind of like shrunk in the middle and it wraps into a cylinder. And then if you go at a 45-degree angle, you can get like spirals.
Would it be easier to stretch those back out? Because you have the outside stretched out.
Yes, so that's another way you can get it to unfold. So you can put ink on the top, you can get it to fold this way, and then you can have ink on the back, and you can get it to fold back. But then after you've done that, it's like letting a rubber band go, it won't fold. It won't come back. But that's okay, there's not much.
So how do you deal with impedances, like especially at a high frequency? You talked about using it as an antenna. How do you deal with that?
How do we deal with that?
Does the impedance change as you stretch uniformly?
Well, it does, but essentially like any other antenna that changes the magnets. Clearly, you need to make a budget when you design a system for that. But you do so in any other configurable system. Anytime you have, like, in some of your wireless devices, antenna, if you change the multiple frequencies, the pins need to get taken into account and change accordingly. This wouldn't be any different. The exact same. That would
Perfect. Just what I was saying.
You know, I have to share a little secret with you. They're not cold hearted individuals. Is that the reason why there's no wow on some of your movies with antennas is because at least show before, you know, one of my seminars already did.
So I can guess.
Yeah, you can impress them. I know that I saw from your stare that I said, wow, these people are unmovable. And I'm so sorry, I should have warned you before that you were actually awaiting some very prepared students in front of you, but you're not very advanced. Yeah. Any other questions? Maybe one more question? Do we have one more?
So the Memristor that you have out there, those two hydrogels. Now the acidic hydrogels are how acidic those?
pH is about 3. Yeah, so the oxide layer is stable at pHs between like 3 and 10. So it's actually pretty stable. So you have to get a pretty high or pretty low pH to remove it.
So maybe 1 or 2.